continue. Okay, so welcome everyone to this webinar, and we're going to be covering the beautiful and wonderful world of geosciences. So I said the science of everything. It's not entirely true, but let's say the science of everything regarding the planet, and also when we look outside of the sort of like solar system and we're studying other planets. So it's quite a big sort of overarching umbrella term for looking at everything to do with that kind of process. So let us start off with the simple question I asked you guys in the sign up, and is porridge a soup? Now, some of you have said yes, and the majority of you said no. So now let's consider this with some actual definitions. So if we look at the definition of soup, right? So Merriam-Webster here says, liquid food, especially with meat, fish, or vegetable stock as a base, and often contains pieces of solid food. Now, with that definition, it kind of seems like, well, maybe porridge is not soup. Let's have a look at Wikipedia, for example, right? So soup is a primarily liquid food, generally served warm or cold, that is made by combining ingredients of meat or vegetables with stock, milk, or water. Now, when we get to like the overnight porridge oats, with salt, maybe we can argue that this definition is a little bit more vague and makes the case for the potential for porridge to be soup. So that's why it's very important when you're doing science that you understand and realize where the definitions are coming from and what definitions you're using. Okay, so if we now go to the next slide and look at the classifications of soup, right? Again, I honestly don't know how I came across this picture, but I'm so glad I did, because look at this, guys. I mean, there is all these varieties of soup. I'm not a huge soup fan, but evidently this picture shows otherwise. But let's just say, like porridge is in the category of thick soups if we want to go that way. But we also realize, well, the basic soup classification is based on sort of like the thickness of soup, right? Or the viscosity. So we're looking at viscosity, okay? Now, actually, something to do with geoscience and not porridge. So we've got the picture of Mount St. Helens and a Hawaiian lava flow, right? So they're both volcanic eruptions, but they both vary in the eruption styles. Now, why are they different? And the real reason here is viscosity. And again, as a geoscientist, volcanologist, geologist, I would be looking at these to then further understand the processes involved. Now, let me explain myself. So, magma is the material, the liquid material that's underneath the surface, and then once it erupts, it becomes lava, right? Just that you understand those concepts. Now, the viscosity of lava, we've got silicates, right? So things like quartz, they are very long chained silica molecules that are strung together. And if there's a higher amount of silicates, it means that the substance, the lava, is more viscous, right? Volatiles, things like water. I love crystals. Volatiles, things like water and carbon dioxide, they will actually reduce the viscosity. So if you think about treacle, it's a very viscous liquid, right? If you add water to treacle, it makes it quite runny, right? So that's the kind of analogy that we have here. Now, temperature plays an important role as well. So again, if you have honey, it's quite viscous at room temperature, but if you heat it up, it becomes a lot less viscous, becomes more runny. Okay, crystal content. Now, when the magma comes up and then erupts as lava, during that process, depending on how long the magma stays in there, it can start to crystallize, right? So if we take an analogy of, for example, like, you've got your water, you start pouring the water out. It's just going to flow everywhere. But if you take like a slushy, you know, that you get at movie theaters or something, if you pour that out, it's going to be a little bit more viscous, right? So like the slushy is the analogy of like a high crystal content in the magma that's erupting out. Now, what we actually want to understand is like, where do we get the different sources of magma from? And this is obviously a very simplistic model. I drew this myself, so apologies for the horrific skills, but this is what you're going to have to deal with. So let's focus on the right-hand side of the diagram where it says Mount St. Helens. Okay, so we have two plates. Okay, we have plate number 1 here on the left-hand side, and it's going down beneath the plate number 2 on top of here, above Mount St. Helens. Now, the volatiles, again, things like water and carbon dioxide that are in the downgoing plate are released into the asthenosphere, right, which is a part of the mantle, and actually lower the melting temperature of the material there, and actually produces a melt that is a lot more silica rich. And by melt, I mean the magma and the lava, which will then erupt out, right? Causing a more explosive reaction, okay? If you picture, for example, when you're cooking something and it's very thick, right? Very viscous, and you're boiling it, all the bubbles that form on the surface and then pop open, and then, like, you know, when you're cooking, let's say like tomato soup or something, right? And then sometimes you get splashed with some tomato juice on your nice shirts and whatever, right? So this is a kind of equivalent of, because it's more viscous, the eruption style is going to be more explosive. Whereas now if we look at the left-hand side of the diagram with Hawaii, here we've got melting that's a lot higher temperature, and it's going to melt slightly different material in the asthenosphere. So we're actually going to get silica poor magma and then lava eruption, okay? And that's going to be a lot more runny, a lot less explosive, and that's kind of what we see in Hawaii today, okay? So let's go on to the next slide. Now, as a geoscientist and a volcanologist, it's very important to understand viscosity, fluid flow, and how these fluids interact, or the lava flow interact with the topography, with the landscape, with, in this case, like a small village, okay? So we have the lava flow going in and around this small town, and you can see how the lava is actually being redirected, okay, and moves in certain manners around the houses, okay? Now, if I'm a city planner, okay, I want to create a city or like a village that's close by a volcano, and I need to know exactly what orientation of the houses I want to create some safe spaces. For example, these green dots here are actually spaces that are safe. So if you were to evacuate your house during a very fast lava flow, I know I need to be in these green spots in order not to actually get burnt alive, to put it simply. So again, here you've got some lava flow that's kind of going across the street, and this is something that we see often in...
What about, excuse me, but what about the volcanic gas? Wouldn't the gas and the ash be coming down too?
Yes, so that depends on the eruptions. Very good question, Jennifer.
I'm also the one who said about the crystals.
Quartz
Crystals always seem to form into crystals with 6 sides.
Yeah, okay.
I made that observation on my own.
Oh wow. Okay, we can talk about that in a little while, because we have a very nice sort of array of pictures later on, and then we can discuss this. This will be really fantastic.
Pictures.
But so yeah, as a geoscientist, I would be looking at, you know, how the viscosity of that fluid moves throughout the landscape to make predictions and, for example, make maps of security.
If I could quickly interrupt to answer your question, Jennifer, about the volcanic gas. Often these safe spots are often used to store expensive equipment that is difficult to replace and evacuate. For example, if you have hospitals, you would put supplies of expensive, difficult to reproduce equipment on these spots and then evacuate yourself.
Like,
So,
I
yeah.
kind of, for some reason, I thought that they would be used sort of like evacuation routes.
Yeah. So again, with these green dots, you can then obviously, if you have multiple green dots in a row, you can then plan and create evacuation routes. Again, to come back to also the gases.
Why not make these big, huge pillar sort of things to divert the lava if it comes down?
Yeah, so like there's lots of engineering projects. So if I actually go to the hang on to the next slide, I can show you. So Geosciences, right, incorporates a lot of different disciplines, as we mentioned in the material that we provided to you, and engineering is a great example of this. And this is a very, very great example that you brought up here. So these pillars and structures, there's lots of research going into right now. Structures that are designed to divert lava flows to actually protect property, because obviously during a lifetime, when you live in places like Hawaii, etc., you want to build a house and you want to protect that. You don't want to keep having to reinvest in making sure that you have to build up your house again after it's been inundated by a lava flow, because these can be they can vary in speed, but they're like like a slow person walking. So it does kind of come at a very fast pace, and especially sometimes the volumes are quite a lot. But yeah, the gases sometimes depends on the eruption type, and also depends on the composition and the amount of volatiles that are actually in the lava. So if you have a lava that contains a bit more like sulfur dioxide and other things like this, you will then get a more dangerous lava flow. But if it depends on the exact eruption style and composition of the lava. But yeah, to come to this point now, so I really appreciate the questions. And again, anyone who has questions, just interject at any point. That's absolutely fine. So yeah, definition of geoscience. I just wanted to come to an end for this topic particularly. So here, for example, in this case, I've talked about volcanology. So we're talking about things like chemistry, physics, maths, and again, engineering and sociology, because obviously we have to understand how people react to you giving news, or how people will react to, okay, no, I don't want to move from my house because I've lived here for so long. So it's understanding how people work as well. And obviously nowadays there's a lot more computer and informatics processing involved. Okay, so data handling, data processing, so things like computer models and maps produced digitally. So that's something that's coming up and coming more and more in geoscience and in most other fields. Yeah, but as a whole, this is kind of my interpretation of the spread of different disciplines that geoscience borrows from. I'm just going to admit that person. So yeah, and here it says, it's not just about looking at rocks, not just looking at volcanoes, or that's what we started off with, funnily enough. We're looking at natural resources, water, ecosystems, and everything is really interconnected. And we're actually going to now cover loads of different topics to help you understand exactly what geoscience is about and what is actually possible today. Okay, so if we move on to our guest speaker now, Nils. I'll just do this there.
Oh, it's me now.
Yeah.
There we go.
Yeah, perfect.
So yeah, Leon did the introduction and covers base volcanology and what if you do with a geology degree and then get to the volcanoes. I just want to take this example to kind of show what environmental geoscientists do, which is now a big part of what people in the geoscience department are doing right now. So, simple question: will global warming lead to warm weather in Scotland? Well, actually, quite curious to know what you guys would think about it. But we poll, and then we'll see how it goes. Obviously, this kind of question has been there for a while, and well, there's quite some debates, and there's obviously long answers, short answers, and we're going to go with a medium long answer to try and understand how it goes. But especially why I'm going through this is to show you
because global warming can cause temperatures at both extremes, so I don't know.
Yeah, well, we'll see. We'll cover that, and then we'll see.
Like
I'm just going to try and show the thought process
weather
behind.
systems up north
Um,
causing stuff like the beast from the east and that, and whatnot, causing stuff like the beast from the east, causing
yeah,
others.
so Jennifer, you're already touching a good thing. Yeah, we need to look at the bigger picture,
It could
Yeah.
disrupt
and then we'll see.
weather systems, causing colder weather, or
Yeah.
causing weather at different extremes.
Yeah,
Because right now
exactly,
it's
exactly.
half. All right, so if we just stop the poll now, 3 people said will be warmer, 2 colder, 1 I don't know. So basically, we just need to figure it
Now
out.
it's 50-50.
There you go. All right, 50-50. Well, we'll see.
Yeah.
So, simple question, but we'll try and figure out. So first of all, let's try and understand how the situation is right now. Ian? Next slide.
Yes. Sorry, I was downloading.
Yeah.
Blue.
Ian is in charge of
Apologies.
my slides.
Can you not? You definitely can't.
No, I can't.
Okay, there you go. Sorry about that.
There we go. So yeah, so first of all, let's just look at Scotland, and you're saying the first thing we're going to look at, or think, is that, well, latitude, so how far we are from the equator towards the poles, is going to be the main, let's say, climate zone we're going to be in, and then dictate the temperatures. And you would be quite correct, except it's more difficult than that, because obviously, if you compare to stuff that's at the same latitude, you get a whole range of different temperatures. Like, for example, the example I put in of Nain in Canada, which is the whole province, if you look at the average temperatures on winters, it's at minus 13 degrees. We don't get these kind of temperatures in Scotland, especially not on average, with often goes to minus 40. Why is that? Why is it that we are the same latitude and we are overall warmer than Nains? Well, you've probably already heard this, and for those who don't know, but obviously the ocean plays a huge role in moving heat and so affecting climate around the Earth. And we're going to go into a bit more detail on this, but the reason is that the water has a way higher heat capacity, and which means that it will basically carry heat for a way long period of time. It will be more difficult for it to change heat. So if there's any process that can bring heat from the equator to Scotland and keep that heat, well, that will greatly affect the climate. So the thermohaline circulation, a big fancy word that just means the movement of currents in the ocean that are regulated by temperature and salt, which we are both, we all know what temperature is, and we all know what salt is. So why is that? Well, it's because ocean currents are very often, or mainly driven by temperature gradients, temperature, salinity, that increases density. So density is the one main part. And then you have other forces like Coriolis forces, Ekman transport, and we're not going to go over these. This can be way too long if we go over these two. So we're just going to look at density for now. So on the graph that's on there, you can see that temperature, if the water is warmer, then the density decreases. And if salinity increases, then the density increases as well. And we're going to just try and remember this, and we'll come back to this graph later on, and we'll see why this is important. So move to the next one. Yeah. So there we go. This is the accepted thermohaline circulation. So the big driving ocean circulations around the globe and how it kind of works. So everything that's in red, the red arrows are the currents of the surface water and the blue arrows of deep water. So as you can see, you would have at the equator the surface water heating up, evaporating, and then concentrating the salt in the surface water that has been left there. So you have quite saline water, but it's very warm, so it will not sink yet. The surface water is next to the atmosphere, and so big trade winds will kind of start moving it about. And if we, for example, look at the Gulf Stream, so the red part here in the in Northern Atlantic, it will go all the way to the north. So now imagine you have salty surface water that goes to the north, and then it cools down. That means you're going to have cold and salty water, which is going to be way more dense than what's around it. And this is why it's at close to the poles that the surface water will sink to the bottom. So there's 3 big places on Earth that kind of drive this big water circulation, or these places where the top water actually sinks down. So it has been observed that actually if the rate at which the water can sink kind of dictates the speed of all the main currents of the globe. So what will happen with global warming? Will that change the circulation? Well, let's just zoom up of the Gulf Stream. Yeah, there we go. So I'll just put a composition like of salinity and temperature characteristics of one water body on there, and we'll see what happens if you have an increase in temperature. Well, if you increase temperature, the density lowers down a wee bit, just a tiny bit. But remember, these three sinking points are close to the Arctic and the Antarctic, where you have massive ice sheets. So if you have warmer temperatures, the ice sheets will start to melt way faster, and they'll release a lot of basically fresh water that will stay on the top surface because they're very low salinity, and they will start to mix. So this will actually reduce the salinity a huge amount to the water that comes in. So we end up with water that's way less saline and warmer, which means that we have a water that's way less dense. Well, what does that do? Well, if you have the surface water, which is way less dense, way more buoyant, then it will be way more difficult for it to sink, which means that it will slow down this whole circulation. Next slide. Yeah. So if you look at the top two dots, especially focus on the top one, it will be way more difficult, way slow for things to sink in, which means that the Gulf Stream, which is bringing out this warm water, if it slows down, it might not reach as far north, or it would just be quite slow, allows the water to cool down before it reaches Scotland. This here will then lead to actually colder temperatures overall, and it is theorized for now and quite widely accepted now in the school of geosciences that actually overall temperatures will be way higher, but for Northwest Europe, which, well, Scotland is part of, geographically at least, will have way colder temperatures because it will outbalance the overall temperature increase.
Wait,
Well, there have been evidence for this in
that
the
means I'll
past.
have to say goodbye to relaxing in my garden. Sunburn? Oh, come on.
Maybe if you move back one slide, Ian.
I blame humanity for this.
Yeah, I mean, you'll see, because it's a whole change in climates, because obviously this will change as well, because if you have less warm water coming up, we'll kind of have a change in rainfall as well, which is directly linked to the ocean temperatures, as well as, well, the trade winds, but trade winds wouldn't really change. Well, maybe they would, but they probably would. But we'll have to see how it all shapes up, to be honest. What I just wanted to point out before is that this whole theory, this whole model does not come out of nowhere. There has been evidence in the past of such events happening. If you're still interested in this, just look on Hendrich events. They are just basically big events that I've seen since the last ice age, where big glaciers, especially in Canada and Greenland regions, would actually melt and cover the top of North Atlantic by fresh water, and that will basically stop this whole thermohaline circulation. So this has happened in the past. There's no reason for it not to happen again. So in conclusion, will it be warm in Scotland? Probably not. And so it's not really going to be global warming. Yes, on average, temperatures are going to be higher, but it's going to change the whole climate as we know now. So if it's colder, is it better? Probably not. It's just going to be that we're going to have to adapt, and plants, crops will have to adapt as well. So this is one example of a whole thought process that basically, if you're doing in environmental geoscience, you will look at all these processes. And all of these were actually quite simple concepts, right? But it's just how you kind of try and link everything and see the big picture, which is the interesting part. Oh yeah, next thing, because we're talking about the ocean and global warming, let's talk a bit about CO2 in the ocean while we're at it. Probably heard CO2 is increasing. in the atmosphere. I mean, I don't think I'm, saying anything new at this point, but it has been recorded quite well since the 1980s. So the red curve on the graph is actually the best recorded CO2 measurements in Hawaii, and the same station also tried to record the surface seawater CO2 content. And you see it's been steadily increasing. Well, nothing surprising here. What might be surprising is the bottom line, because they all did the measurements the whole time, and the pH is decreasing. It means that oceans become more acidic. Maybe you've heard this already before, but again, we try to understand why is that, and try to get some methods to see that. So next slide. There we go. So Henry's law, you might don't remind too much. The idea is that CO2 at a gas and fluid boundary, there's chemical exchange, and well, if you have increased CO2 atmosphere, you're gonna be dissolving with coefficients CO2 into the ocean. Well, why is CO2 is not acidic by itself, right? So there needs to be other stuff at play. So there's a whole series of equations, actually of chemical reactions that happen in water. So when CO2 is added to the water, it becomes aqueous CO2, and it will react with CO2 to form carbonic acid. Well, carbonic acid is a very strong acid. It will just react out and become bicarbonate ions. During this reaction, it releases H plus ion, a proton, and actually it will also react even further and produce carbonate ions sometimes. So all these reactions release hydrogen into the seawater, which will, at the end of the day, just increase the acidity of the ocean. Now, why are these equations important? Is because actually they are regulated by quite a few factors. They're regulated by pH themselves, which kind of makes sense because they have H plus ions in those reactions, but they're also affected by temperature and all this. So right now, the composition of the ocean, like all the CO2 that's in the ocean, is basically in bicarbonate ion form. There's less than 1%, which is as actual CO2, and bicarbonate ions are 90% of the inorganic CO2 in the ocean. Well, why is that important? Next slide. There we go. Well, as you probably get, is that if you get more CO2 in the ocean, all the reactions before are going to be like shifted, and it will start to actually release a huge amount of H plus ions and getting more acidic. Well, I'll just put up the equation for calcium dissolution, and calcium dissolves with acids. Well, here H plus ions just reacts to make aqueous calcium. So any living organism that's producing shells is going to be way more difficult for it to produce it. So, for example, the poor nautilus can have a harder time doing it, but it should still work. The reason why lots of geoscientists worry about the acidification is about the plankton, as they're the base of the food chain for a huge amount of what's the marine life. If it's more difficult for them to create their shells.
Oh no, the plankton. Are they trying to steal the Krabby Patty formula?
Yeah. Well, actually, they're more like giving food to the ocean on huge scale.
I was trying to be funny. I was trying to be funny.
All right. You've probably heard of coral bleaching as well. Well, corals also have this calcium structure, so it's more difficult for them to make their structure, calcium carbonate structure, when it's more acidic. But coral bleaching must not be directly associated to acidification, because corals themselves are symbiosis between an algae and actually a microorganism, a wee animal. And they are very sensitive to temperature changes. Well, I would say with climate change, the seawater gets warmer. Well, what does warmer water actually mean for this acidity stuff? Next slide. There we go. So one thing that I haven't mentioned yet is that dissolved CO2 is way more difficult. CO2 cannot dissolve as well in warm water. So if the water gets warmer, it will actually start releasing CO2 back into the atmosphere and kind of inverting Henry's law again. So with the ocean getting warmer, especially, I mean, the surface ocean, there is this risk of actually having a feedback of basically the ocean pumping out CO2 back into the atmosphere. Next. So this is the loop that's dangerous to come into. This is also, again, why Stant is worried about that. Is that if there's more CO2 in the atmosphere, gets warmer climate, surface temperature gets warmer, then the CO2 gets less soluble and gets put back into the atmosphere, and then it just loops around. Now, I mean, this one thing that comes off from this graph is that, well, the Earth is 4.5 billion years old. It must have happened at some point in the past. Why has it not just run away already? Well, there is actually one way to break this loop, and one big way to break this loop is erosion. For those just ideas, if it gets way warmer, you have way more evaporation, way more rainfall, all that rain and way more ice, glaciers grow up as well on high altitude stuff like mountains, and they will erode down and basically break down the mountains and have a big input of back material that will go back into the ocean, like calcium carbonate and stuff like this, which will actually help balance out the CO2 in the ocean and reset the acidity. The problem is, for this blocker to come into place, it takes way longer timescales. This goes over hundreds, thousands of years. So it will be the acidity of the ocean will be fine, but it will take 100,000 years to get back. This is what's more worrying about it. So again, this is another example of what environmental geoscientists actually look at. Lots of chemistry, mostly chemistry, and then linking in some physics aspect and looking at how actually everything kind of links together.
Yeah. Oh, and also biology as well. So biology is a big.
Oh yeah, it's huge. Yeah.
Well, thank you very much, Niels. Niels will be coming back in a later segment as well. I will take over now, and actually, I'm going to talk about something I've done, some field work. So a couple of years ago, I did a year exchange in Calgary, that's in Canada, and so that's what Calgary is. And Calgary is basically at the forefront of the Rocky Mountains. So it's very much associated with geology on all levels, right? So this is the University of Calgary, the library. And you can see some little ducklings walking there. I took a picture a while ago. But yeah, so...
Aren't those geese? Aren't those geese?
You are correct. In fact, those aren't geese. I apologize. Those are in fact geese. Thank you for that. But the main point here is Calgary, the city, is very big on oil and always has been for some degree because there's lots of oil fields around. So it's kind of known as the Texas of Canada. But it's a very, very beautiful place and lots of beautiful people. Why am I telling you this? Well, I did some field work there, right? And fieldwork is really cool, really exciting. So the first time I got there, 2 years ago in August, you know, this is the first field trip I went to. You know, I arrived 1 week, and then the second week, once I arrived, I did some field work, 2-week field work. And it's a very beautiful landscape. You might be thinking like, oh, why is it so hazy? But let me tell you, those hazy skies are actually smog from all the forest fires, because British Columbia, which is the province next door in the Rocky Mountains, etc., we have lots of forest fires annually. It's a very normal process that occurs. It's a very controlled process, but obviously the pollutants are what sort of haze up the sky. I think it's beautiful, but it also smells a lot like burnt pine. But anyway, that's beside the point. Again, this is a very nice area. Same area. You can see that these pictures were taken at a different time of year, so there's no more haze, right? So this is taken actually during winter time. Springtime, the year after. Here we can see all these beautiful layers. So you might have heard about layers, you know, sedimentation, all this kind of processes that occur, very important in geosciences. And the red lines here just sort of symbolize and show all the different layers. You've got this sort of like pale beige layer at the bottom, and then it builds up slowly bit by bit to the sort of darker band and then lighter band. And that tells you a lot about sedimentation rates, you know, like what kind of environments there were. So this environment used to be a sort of like a cross between a river and an ocean. So it used to vary between the two. So that's why there's all the sand here, basically. Again, on the left, you see these beautiful carved up landscape. A lot of this, sort of these plateaus at the top are from glaciers. That's kind of carved the landscape up and flattened it at the top. And at the bottom is kind of carved in a little bit. Those are rivers, etc. That's further erosion. On the right, you see pictures of, they're called hoodoos. So if that's the first time you heard it, well, good, because this is the first time I heard about it as well when I got here. Now, these are quite interesting features because they form through wind erosion, right? So removal of material via wind, and the wind picks up small pieces of grains and then sort of bashes them against it. And you can see that in the middle segment, sort of where the hoodoo sort of bottlenecks, that's the weaker material, and it's easier to remove this material than the top part there. That's why you get like these little mushroom tops. I think that's really cool. Also, when you're just walking around here, this area is very, very, very well known for fossils. Okay, so I was just walking here and found the shark tooth. Right, so I thought that was really cool. I was like, oh, wow, you can find fossils like that. It's actually the 5th best place in the world to find fossils, from my understanding. And so much so that you had this guy in the 1980s go down a river, just fishing, just like the one here on the right. And after a big storm event, he saw these bones poking out. And actually, he found the 14th best preserved dinosaur of a T-Rex, skeleton of a T-Rex in the world. So, and this is in the Royal Tyrrell Museum, which is actually located in Drumheller as well. So I went to see this myself, and they've got some spectacular pieces there. It's wonderful. Again, as a geologist, you go out, you do field work, you do interesting activities, you find out about the local geology. This is what you do. Okay. Now, what else did I do in this 2-week field trip? Because I just wasn't everything I did. Okay. So we went to a place called Canmore. This is in the heart of the Rocky Mountains. And we went down this sort of dried up river channel, and you can see us sort of climbing up there, and you can appreciate how much force the water normally has when it's melting season. But right now it's dry, so we were able to walk here with our equipment. Right, so why do we actually go up this path, right? Well, it's to see this beautiful scenery. And if you can actually make out on the top right, I'm going to take my little pointer, top right, you can see these sort of like, they're called beds, right? Again, these layers, and they're slightly curved like this. Maybe this will help. If you can see that, kudos to you. That's really great, because you know, it takes an skilled eye to see these things. Now you might be thinking, okay, what is this, right? Why are they folded? Well, if you imagine you've got these layers, okay, they're deposited horizontally, so they're laid down horizontally, okay, and then you've got these forces, you know, 2 continents colliding together, and then you've got this sort of like folding of these layers, and that's what you get here. So you can see that this sort of middle band here is what's represented here. The top part here, when it curves up, that's been removed through erosion, glaciers, etc. Okay, glaciers kind of move through and remove all those rocks at the top and then slowly deposit them elsewhere. Now, why is this important? Again, geologists and structural geologists use this to understand how mountains form, how rocks behave, how continents move, etc. And we also use this to predict how earthquakes will react and what, you know, exact magnitude there will be, or we can make these predictions. Now, this is also great for, we can apply this knowledge, and we can also apply this knowledge to space and other planets. So we can, if we understand the geology on this planet, we can definitely understand the, you know, geology on other planets, which will help us again find resources, use resources, build structures, etc. Living with the planet. This is one part of understanding how we coexist with this planet. Okay. Now again, that was one part. We went to another segment. You know, it's late at night. I say late at night. It's late in the afternoon. For us, it felt like night just because we did a whole day's work in the field. So we're saying 8 a.m. start, and then this is probably around probably 6 or 7 p.m. At night. And you know, we're actually supposed to, you know, you can see the minibuses in the background there. So we're on our way back, and our professor is like, stops the car, stops the minivan, and tells us to get out, put our hard hats on and our high-vis jackets because we're on the road, so health and safety, right? And he says, take a look, guys. And you know, we're like, I just want to go home, to be honest. I'm a bit tired, so I was like, okay. Looking at this rock, you know, we're looking at it and we're staring at it for ages, and I'm like, what do you want us to look for? Because all I see here is a bit of a gray rock, you know. And then he says, you know, look closer. And I'm okay. I'm looking. So I'm looking and stuff. Well, you see these little things I've highlighted, right? So they're little chunks of other rock inside this rock. Now, that's a bit weird. What is that? Okay, so look up closer again, and you're like, what is this? Okay, and again, you look closer and you realize that it's this. And again, this diagram doesn't tell you much, does it? Let me explain what it is. Okay, so imagine you have mud, okay, very soft, mushy material. You take a pebble and you drop it from high, and it sinks in and it kind of makes a little divot, right, where it sits in. And then if you've got more sediment layering on top, well, that's basically what you got here. So, they're aptly named dropstones, okay? And they're almost always associated with marine or water deposition, right? So deposition of material within water. Again, what? So, okay, this is interesting. Now, you know, we talk a bit more with the professor, and he's like, okay, you know what? I'll spare you the pain. It's a till, and we're okay. I know what a till is. You guys might not know what a till is. So till is actually the sort of end result almost of a glacier, right? You got this glacier or ice sheet moving across the landscape, scouring up, picking up pieces, and at the front it kind of mills everything into small fine powder mixed in with all other jumbled up garbage, right? So loads of rocks. Now, an average sized glacier, you know, ice sheet throughout history yields a till about 20 meters thick. So that's quite thick, right? I'm not gonna lie. That's pretty thick. Now, we take a stand back, and you know, we talk with our professor, and you know, we look down the road, we look up and down the road, and realize that the till that we're looking at is not 20 meters thick. It's 1,000 meters thick, 1 kilometer thick. And you're thinking, what? How is that possible? You know, it's like normal ice sheets produce 20 meters. How can you produce 1,000 meters? Good question, right? So it's called the Toby Conglomerate. And again, it wasn't, you know, vertically 1,000 meters. You know, this whole area has been tilted so that it was like horizontally almost 1,000 meters thick. That's crazy, right? Now, why am I telling you this? It's a good question. So, you know, if we imagine that these glaciers were massive, right? Let's just say, you know, they went out into the ocean, okay? Which is nothing new. We know that glaciers and ice sheets, they move through oceans, you know, and stuff like this. But if I tell you that these deposits were found as far as the equator, I'll tell you something. He's saying, so ice sheets all the way from the North Pole and from the South Pole all the way to the equator. That's weird. That's scary. That's cold. That sounds really terrifying. Now, before I continue on this story, I'm just going to show you a bit more detail on this diagram here, which I drew, and you'll see one little mistake in a second. So again, you've got these ice sheets again, you're carrying these rocks, these little chunks of rock across, and occasionally they will just kind of drop them, hence drop stones, into the sediment, right? Again, that's why we get these patterns. Now, Niels aptly pointed out that, wait a minute, at the time of this ice period, there were no fish, right? It's before fish even existed. So let me just turn off my laser pointer. No fish. No fish. Eukaryotes and bacteria. That's what was there. So very good, Niels. Very good. So yeah, these ice sheets moving out into the equator. What on earth is this? Right? Well, it's called snowball Earth. It's a hypothesis that basically links up the ideas and the observations that we've made and puts it to test.
You said snowball Earth. I was just thinking that. I was about to say that.
See, there we go. There we go. Very good. Very good.
That would be a massive snowball fight. Absolutely.
It'd be really cold, though. I tell you, it'd be really, really cold. So there's a couple of issues, though, because this is still a hypothesis. Okay. Because a lot of scientists actually believe that it's more of a slush ball Earth, because they think that at the equator there was a bit more melting, and I'll tell you exactly how that goes. Because if you've got a planet covered in ice, right, you've got lots of white surfaces. White surfaces reflect light, reflect sunlight, right? So if you've got sunlight shining down and it's being reflected away, well, you've got a problem on your hands, right? Because you're reducing the amount of energy that's actually able to get to the planet and actually melt ice, okay? So you're basically reflecting everything off. Okay, so how do we get out into this kind of weather where it's, I mean, Scotland is still a bit cold, but still, you get what I mean. No, we're not talking about snowball Earth outside when we look outside, okay? So how do we get from here to something else? Well, you've got volcanism, okay? Volcanism at the core produces, again, greenhouse gases, which, that's right, global warming and the melt the ice. And that's why a lot of scientists believe that it's more of a slush ball Earth, because at the equator it would have been enough global warming and climate change to actually allow for the equator to be sort of, you know, warmer. So that's snowball hypothesis. I hope you enjoyed that, because I always found this very interesting. And again, when our professor told us that the rocks we're looking at were actually talking about this, you know, we went from like, oh, I just want to go home, to like, wow, I want a sample of this rock. Like, you know, the whole mood changed, because this is really, really cool. Slightly different story. Okay. Again, I'm in Canada still, and I'm looking at this layer of rock here. No, nothing interesting, really. And it draws parallel to a story of a geoscientist studying clay in Italy. Again, sounds a bit boring, really, doesn't it? Well, you know, this guy, right, studying clay in Italy. His father was a physicist. He was working on a device to measure concentrations of very rare and small quantities of elements in matter, right? So, you know, looking at concentrations of metals and other things like this within rocks or other samples. Okay. Now, if you study deposition as a geoscientist, which you no doubt will do, you will come across the word iridium. Now, iridium is a very, very rare metal that doesn't actually exist naturally on Earth. and the only source of it is from outer space, or the main source, like literally 99.8% of iridium comes from outer space. Okay, so how does it come to the surface? It comes down as small macroscopic rain of small sort of, dust particles, basically. Basically, you've got meteorites coming down, and they're so small that they just sort of evaporate into very small pieces, and then they sort of rain down. Okay. Now, if you have deposition occurring, okay, layers forming on top of each other, the longer the layer is exposed to the atmosphere, the more it is exposed to levels of iridium coming down. Okay. So let's put it another way. If you have really rapid deposition, each layer doesn't have a lot of time with the atmosphere, therefore it has very low concentrations of iridium. So high concentrations of iridium means slow deposition rates. Low concentrations of iridium means very fast deposition rates. Okay. Now, the son, right, the guy who was looking at the clay in Italy, he gave a sample to his dad to test out his machine. And he wants to obviously know what's inside the clay. Okay, so comes back with an iridium being 100 times higher than normal. And the father's worried that his machine wasn't working and he was about to give up, but he gave his sample to his colleagues to test it another time. And it turns out his analysis was correct. This particular clay layer did have an iridium content 100 times higher than normal. Okay, the son was like, wow, this is crazy news. Goes around the world trying to find this exact clay layer as well. Turns out this clay layer spreads across the entirety of the globe and contains exactly that amount of iridium, an absolutely absurd amount of iridium, sorry, not uridium. So we have this. Now, why do we have such high levels of iridium? You're thinking maybe deposition rates were really slow everywhere at the same time? Doesn't really sound geologically plausible, I think. So maybe something else brought that iridium down to Earth. So, him and his dad are thinking, if an asteroid about 10 kilometers in diameter, so, about the size of a city.
The dinosaur are killer.
Maybe you're just going to have to wait. You're just going to have to wait to see what's going on.
Wait, no, but that one, wasn't that one like 6 kilometers wide?
Well, 6 to 10, but from what I've understood, it's mainly 10. But the size itself isn't necessarily that important. They're like the specific size. It's more about the size, like the fact that it's huge, right? And the amount of iridium that it can actually provide us. But yeah, so basically we're thinking, okay, an asteroid the size of a city came down somewhere at some point to produce this iridium layer. Now, at the same time, paleontologists were trying to figure out why the dinosaurs disappeared all of a sudden about 66 million years ago. So, everything from increased amounts of ionizing solar radiation, which caused cataracts in the eyes of dinosaurs, which made them go blind and then die out, to aliens, were all plausible ideas that were thrown around amongst paleontologists. But here comes along this young Alvarez and proposes this hypothesis, because this clay layer actually dates to exactly 66 million years ago. So we have a method, a means of getting to a big extinction event. Okay, and again, this impact caused climate change because all the dust that's been thrown up into the air. It's caused tsunamis, and obviously the impact itself killed lots of animals too.
An apocalypse, basically.
Basically an apocalypse, yeah. In short, yeah. So that's basically it. Now,
and to dinosaurs, we would be living in a post-apocalyptic future.
That is correct. Yeah, dinosaurs are terrifying beings. So I'm glad that we're not living there. But
it seems that now some of them are a bit too chicken.
That's very good. I appreciate the humor, the geoscience humor.
funny.
I appreciate this.
I'm
Now,
funny.
where is the crater though? Right? So that's the question.
Chicxulub, Mexico. That's the
Yes,
one.
very good, very good. But we'll get to how we actually found this out. Okay, so because you might be the one that knows the answers, but not everyone does. So don't spoil the movie.
Sorry, guys.
Well, or the webinar, whatever. No worries.
I really like geology.
I can see that, which is very great. So scientists were thinking, where is this crater? How are we going to find this crater? So tektites, right? Top right-hand corner. Basically, material that's instantaneously molten and flung up into the atmosphere when the object hit the planet. Okay, and they're molten glass, almost like substances, right? Red hot, and as they cool down, they become sort of these drop-shaped objects, black, right? It doesn't really look that drop-shaped here, but you got to believe me that that is a tektite. The other thing that was very indicative of, or is very indicative of any impact is shocked quartz. So you've got quartz, right? And if you bash it really hard with something, the internal structure changes, and that's unlike anything that can produce this. So the only way to produce shock quartz is through massive impacts. For example, atomic bombs, they produce shock quartz as well. So now scientists found all of these near America, right? So now North and South America, right? So these were the main points of where we found these. So we think, okay, maybe somewhere in the Americas. So again, during a semi-routine petroleum exploration in Mexico, a geophysical survey, right, a gravity survey, found an unusual structure, half submerged in water. This was the crater we've been looking for, right? Now, the real thing is, we've got basically a suspect of what killed the dinosaurs, but that's not all, because this. Okay, what is this picture of? This picture is of the Deccan Traps in India. Okay, what are they? Why did I put a picture up here? Okay, well, because the Deccan Traps are actually the leftovers, you know, of a massive flood basalt lava flow event. Okay, which lasted about 5 million years, from about 60 to 65 million years. Okay. So it's continuously spewing out lava non-stop, and it basically produced lavas about the size of France and about 2.5 kilometers thick. So it's quite a lot of volume of material that's been produced here. And again, you can see the layers of these lava flows roughly pointed out by my dotted line. If you don't see it, don't worry, it's not a great picture, but just trust me, they're there. Now, lots of lava, lots of eruptions, and again, mentioned earlier, they produce a lot of gases. CO2, sulfur dioxide, methane, and other potent greenhouse gases, which would have really changed the weather patterns. Things like soot and dust obscuring sunlight, so causing massive amounts of temperature fluctuations for over decades. Okay, and this can also be attributed to the extinction. However, what came first, the asteroids or the Deccan Traps? Well, what killed the dinosaur? That's the real question. Well, we know that the traps came before the impact. Now, the majority of the output, though, this is where the dispute lies among scientists. Was it before the meteorite impact crater, or was it after the crater, the impact? So this is something that geoscientists are still figuring out to this day, is trying to see what exact part did the Deccan Traps play, because we know that they were active at this particular period of time and that they probably contributed to the extinction of the dinosaurs. But whether they were the sole cause, the main cause, whether the asteroid was basically the nail in the coffin, or whether Deccan Traps has nothing to do with it, this is something that we're still working out today. Okay, so geochemists, paleontologists, geophysicists, geologists, environmental geochemists, just are some of the people that work together to actually produce all of this information that we have today, and I can just easily talk to you about. Okay, so these are the kinds of jobs that are associated with finding this research. And again, most of these people involved in these studies, they don't go out in searching for these things. You know, like the first guy who was looking at clay, he wasn't looking for an answer to find what killed the dinosaurs. He was just looking at clay for some other reasons. Okay. Anyway, so let's get back to Canada. Okay, so I'm showing you pictures of these hills. Okay, why do you think I'm actually here? You know, why do you think I'm showing you these pictures of the hills? Because it just looks like a different like a landscape from the UK, doesn't it? Like if I told you that this was in the UK, I don't think you'd be able to tell me otherwise. Now, what if I told you that this was a meteorite impact crater? Would you be surprised? I think you would be, because you'd be saying, wait a minute, craters, you know, look like this. And you'd be right. Now, do you see this? It's called the central rise. And I'm going to show you how it forms. And I'm going to show you exactly how I'm actually stood there, but in the other picture. So we got a meteorite hurling down at some insane amount of speed. Impact, bam, all the tektites and all the debris just ejected up into the atmosphere, into the air, you know, just massive amount of havoc. As you impact and come up, it's almost like dropping, you can almost see it when you drop water into, like a water droplet into water, you can see like the little uprise. That's the central rise right there. Okay, and that's how that forms. Now, if you have a glacier coming across and just kind of bulldozing the whole area, and then you're just left with a little couple of peaks, well, that's what I was showing you earlier. Now, you might be thinking, okay, it's one thing you telling us that this is a central rise, but how do we actually know that this is true? And that's exactly what science is about. If you make a claim as a scientist, you have to back it up with proof. Here's my proof. Okay, so shatter cones. Okay, that's what I'm going to talk about, because you got the impact and the seismic shock travels throughout the rock, and you rearrange the particles and fuse them together into these cone shapes, right? And that's why you can basically take these cones and you can pinpoint exactly where the impact was. So here, this is, if you go up further to the top of those little hills that I showed you earlier, if you go all the way to the top there and you just dig around a little bit, you find these shatter cones, okay? And I've taken the liberty to kind of edit the picture a little bit on the right, just so you can see these sort of like lines and the cones, you know. I hope you can kind of make that out. You know, this is my proof. How can we study asteroids in the future so we can predict whether something will hit us or not? Well, you can study the skies, right? So 3 years ago, I worked with Professor Alan Hildebrand, who is currently working on a variety of projects regarding meteorite and asteroid analysis. You know, so I use this software here to help identify objects in space. Okay, the algorithm is using data from the WISE NASA mission. Okay, and it basically stacks lots of images on top of each other and then takes them away, and that reduces the amount of like black and white haze, you know, noise, that's what it's called, right? And increases the focus on the actual object that we care about. Okay, and then the program says, I've compiled all these images. Is this an asteroid? Yes or no, maybe. And then I'd be just sitting there and just pressing yes, no, maybe. Okay, there's certain characteristics that I'm looking for. A lot of the time, it would suggest something that I think that's just, you know, some lighting effect. So if I did think it was an asteroid, it would just record it down and pinpoint where it was. So also check out the little like picture there. Doesn't it look like a little face or something? I just thought it was adorable, with little like 2 eyes and things. So that's why I saved this image. You know, you go through hundreds of these to get actual data, so it takes hours. And then at the end of the day, well, at the end of the day, at the end of the week, if you work 8 hours every day, you end up with an image like this. So you see all these green trails here. they actually represent actual trails of identified asteroids. So I found these. So they are unique discoveries. The purple ones are maybes, and the the orange ones are the ones that the computer suggested, but they're actually not true. You know, because you can see actually coincidentally they all move in the same direction. That's not a coincidence, but that's more physics that we don't want to get into. So I just want to get a little bit of background. Again, Alan Hildebrand is a very, very cool guy. So he's a classically trained geologist, geophysicist, and he's actually responsible for linking the geophysical data that I was mentioning earlier in Mexico to the meteorite crater that killed the dinosaurs. So he's actually kind of a bit of a science celebrity. But however, his recent work, if you follow science at all or NASA, he was working on the OSIRIS-REx mission, right, to the asteroid Bennu, and which I think is really cool. But basically, he was responsible for kind of creating an analog material used for the sort of lander legs, so that the probe can basically take a sample from the asteroid and then fly back. So this is, again, something that geoscientists are involved in. They basically create mediums to help engineers, etc., because we understand how rocks work. We understand how material behaves in space on Earth. We can produce and reproduce these kind of data. That's kind of very important also for NASA. All right. So that's enough of me talking on for ages. And now Neil's going to take over a little segment which again talks about geophysics. So anyone who's interested in sort of physics and maths, and this is like down your alley. And at the after this, we'll just continue on. It's basically just a picture slideshow of some cool things that we're going to discuss. All right, I'll hand over to you, Niels, for a while.
Yeah, thanks for these stories. They're actually quite cool stories. We were looking through that for a while, and you were leading things with like space and physics. So well, I'm back. More math. There we go. Yeah, that's right. Less pictures, more math. That's physics for you. Yeah, I just want to.
So gravity is uneven across the country. Are you saying?
Sorry, the maps I've got there.
So are you saying that gravity is a bit weird in some places?
Yeah, I was just because I think you've all probably heard that gravity is constant. I mean, on Earth you have the gravitational constant.
So what do the red colors mean? Is there more gravity or less gravity?
Yeah, well, we'll go through. And you'll find out. I mean,
I might want to go to these places and see if I can jump or feel any noticeable difference.
I mean, on paper you should be able to. Whether you're gonna feel it or not, I don't think you would.
Or see if I can throw a ball and measure how fast it can fall down and then clumsily hit me in the face.
Keep that idea for measuring stuff, because we're gonna go over how we do measurements. And you might have some good ideas to how we can measure stuff good. So yeah, as the map kind of shows, and Jennifer pointed out, well, gravity, even though it's often assumed to be a constant at the surface of the Earth, well, it's not. There's very small variations. You wouldn't be able to feel it. It's way too small. But why is that actually useful? Is because geophysics and geophysicists, well, try to use physics to get more information from the Earth or any actual planet while we at it. But let's just focus on the Earth first. And well, the issue is with the Earth is that we can't really go that deep, and we can't just take a sample of everything, and we can't just dig everywhere to get some ideas. So we need to come up with other techniques, other methods to actually have an idea of what is going on. I'm going to go through the example of gravity, but there's plenty more. Anything that has to do with electromagnetics, anything that has to do with seismics, with waves, but this will be way too long for a seminar. So let's just take gravity, for example, and stick with it. So gravity is, I mean, for what we're going to play with today, gravity, that we'll assume it's a force. And force on Earth, if you want to know the gravitational force we have, you take your mass, the mass of the Earth, times it by the universal gravitational constant, the big G, and then divide it by the distance you are from the center of the Earth, so the radius squared. Well, you've probably seen this already in physics class. And well, little g is the gravitational constant at the top of the surface of the Earth. And as you see in the bottom equation, well, it depends on the mass of the Earth and the radius of the Earth. Well, if we assume everything to be constant, then it is constant. But if there's any variations in mass or any variations in distance to the center of the Earth, then there's not a constant anymore, and we have to actually see and measure it. So yeah, geophysics often they're just coming along while geologists are just having fun and just moving about all things that we assume are correct or are constant, and they're not. So yeah, this is one of them. So how would we actually try to correct? What would actually cause the mass of the Earth to change, or the ratio of distance and isotope to change when we make a measurement? Next slide. Yeah. So first of all, when you make a measurement of gravity, we need to correct for lots of stuff. Let's correct for the latitude. Why would gravity change when you are at the pole or when you're at the equator? Well, first of all, the Earth spins. It's spinning around, and so you have this let's call it the centrifugal force. We'll go with that. If some people are picky, they'll tell me it's not a force, and I will acknowledge that, but we're not going to go in detail in this yet. So we have centrifugal force at the equator that will literally counteract the gravitational force. So this will have an effect that gravity should be slightly stronger at the poles than at the equator. But is that all? Because actually, if you see in the bottom picture, well, the Earth, even though it's rock and it's quite hard,
round. It's not actually spherical.
That's it. It's not actually spherical.
It's oblate spheroid. So
yeah, so we usually have, this is the model of the ellipsoid.
flat earthers and round earthers are wrong. I'm an oblate spheroid earther then.
Yeah, well, you know the term's good, because even this is simplification what I've got down there, because it has all ups and downs, but on average it looks more like a flattened balloon with at the equator, because centrifugal force being like elongate and the poles being like squished down and shorter. Well, this means that at the equator you are further away from the center of the Earth. So remember this r squared, the radius squared? Well, if you're further away, this has changed already. And same thing goes that you're going to have more mass under your feet when you're at the equator. So the mass actually will change this equation again. So the altitude variation will basically try and see all these variations and just combine them all. And overall, because some of them kind of balance each other out, well, overall, you have higher gravity in the poles than the equator. So there are models to try and counteract for that. So now you got to measure your gravity measurement. You applied the correction for the latitude. Do you have a constant? Well, not yet, because there's still more things to look about. If you move to the next slide, yeah. Well, topography. It's basically similar to what we talked about earlier, but on a smaller scale. Because obviously, when you're on top of the mountain, well, you're further away from this model you made before, the red curve on the we diagram on the bottom right. This is the model you'd have after you've corrected for latitude and the shape of the Earth being not spherical. Well, if you're on top of a mountain, you're still further away from this, so this is also going to skew your results. And this is called a free air correction, by the way, if anybody asked, whatever. But then you have also a whole mountain underneath your feet.
So if I was to throw a ball on top of a mountain, it would take a fraction of a second longer for the ball to come back down and hit me in the face.
Well, technically, yeah, because when you're at a mountain, even though you have extra mass under you of the whole mountain being quite big, well, being further away from the center of the Earth is going to have a bigger impact. So technically, there's slightly less gravity when you're on top of the mountain, and that's all because of the v square. That's next to the distance here. So yeah, if you're on top of a mountain at the equator, you'll have less gravity. You can throw your ball higher, let's say, than if you do the same force at the North Pole.
Higher and then wait a tiny bit longer before
Yeah.
And then I get my glasses knocked off of my head by my own clumsiness.
Yeah. Even though you wouldn't really be able to feel it because these measurements are tiny. Tiny, tiny, tiny. Well, after all of this, if we've corrected for latitude, if we've corrected for topography, now we have a constant, right? Because the mass and the distance is not going to change anymore. Well, maybe not. Actually, after you measured gravity in lots of places, and you've corrected for latitude, you've corrected for gravity, and you think you have a constant, and there's no point measuring stuff anymore, everything should be the same, right? Well, you end up with maps like these, when you clearly see the gravity is not a constant. So what is going on? So technically, every time we talked about this extra mass under our feet, it was always, oh, there's a mountain under our feet, so there's more rock, so there has to be more mass. Well, we can't really just say there's more mass. We can say, oh, there's more volume of rock, which we assume will get to more mass, but no, there's more volume of rock. And if the rocks are the density we assume they would be, then there will be more mass. Well, obviously, all that's left now to correct for is the actual density of the rock just underneath. And the effect of this is all going to be felt in the first 100 meters, really, or hundreds of meters. So you really can kind of scan the top surface of the Earth and see for all the variations in the rock types. And this is actually quite useful. If you you probably won't recognize from here, but if I tell you that the yellow circle is Arthur's Seat, and the blue circle is Blackford Hill, for those who know Edinburgh, well, you can see there's a big change going all the way through Edinburgh from these measurements. And that stuff have nothing to do with building a road and stuff like this. This is just because there's two very big changes in the rocks that are under our feet. There's a big fault. This is actually a very good way how geophysics help geologists and scientists locate stuff. Easy, because you can put instruments on the plane, go over a whole county, and then just map out all these changes in gravity, and then, oh, there's something interesting over there, and then look in more detail. So how do we actually measure all this? So you can just put it in the plane. If we go to the next slide, we can see how we actually measure gravity. So, as Jennifer was saying earlier, a mass and a spring. That's quite easy. You measure this, and if gravity is stronger and you haven't changed the spring, well, then the mass will just drop lower. Problem is, this is all relative. We said lower, it doesn't give us an actual number. We need to actually have a way to compare this. So the wee box we see being used in the field there has actually just a mass on a spring being extremely precise and can measure tiny changes in gravity. And these need to be calibrated with actual absolute gravity meters, like the one at the top that's being used. And there's like a few per continent, and I think there's like one in the UK. They're just dropping stuff in vacuum and measuring the time it takes to fall down, and they have an absolute measurement of gravity, and it varies. So this is all being put in field. So if you can put the same kind of instruments on planes, go over big areas and have a rough estimate, and then you can go in the field and actually measure more detailed stuff, and can find like if there's something missing, if there's very low densities, maybe there's a water reservoir, maybe there's oil, maybe there's salt. If the density is way higher, maybe there's actual ore, you're not going to go like mining every single mountain you see until you find something interesting. You're just going to go once with the plane over, then once you go by foot, and then you narrow it down. Well, even better than narrowing it down by plane, you can use satellites. So the latest one is actually a satellite has been sent in the, I think it was 1970s, 1980s. There's been two of them that have been sent. And actually the accurate the position where they are, because all the wee reflectors on it, they were used to kind of shoot at them with lasers from the Earth and kind of reflect, so we can triangulate the position of it very precisely. And this is orbiting around the Earth, and the orbit of this will be affected by gravity. And this is how we kind of mapped out how kind of the Earth's shape was kind of first idea of the Earth is not a sphere, and it's again exact the shape of it. and that helped doing all the corrections I talked about earlier. Well, if I can do this for the Earth from a satellite, we can probably do this for anything. And so they made gravity surveys of the moon. It's the closest thing that's not the Earth that we can actually experiment stuff on. So sent the same kind of a reflective ball on the moon, measure the position, and there we are. After a few years of running around, you have this very precise gravity map. And so this is just, again, one example of how geophysics actually kind of works these days. And they say, oh, let's try and figure out something that we think gravity is constant. Maybe not. Maybe there's more to it. And then try and deconstruct it. Try and understand all the parameters at play for it. And then find ways to actually be able to sit back in the lab, not doing much work, and just looking at data from satellites and have all the data. Easy. Making life easier for yourself. Lots of geophysics data now is used in outer space. So if you think of most discoveries that are made with NASA, like, okay, is the water on Mars, for example, this kind of question, these are often answered by geophysics techniques being put on the Mars rover. I mean, right now they have a few electromagnetic surveys going on the rover that's on Mars right now. And this is it. And some people are just starting geophysics and end up with NASA. If you fancy doing something like this, go for it. There's plenty of options. It's great. The Earth is still difficult to understand, and obviously we all need geophysics right now as well. So yeah, I hope this helps you guys get an idea of how to apply physics to the Earth. This is one example, but I'll tell you there's plenty more. That's it.
Well, thank you very much, Nils. That was actually really intriguing. Yeah, so continuing on, we're almost done, guys, in case you guys are like, oh my God, how long is this going to drag on for? Don't worry, we're almost done. So fieldwork. Okay, I've touched upon it a little bit. Nils has touched on it multiple times as well. Why do we do fieldwork? Right, we do fieldwork to gather data because we can't just do experiments just in a lab. Some of us can, but most geoscientists, again, because we study the complex nature of all the interactions in the world, we have to actually go out and see them for ourselves or get data back to our labs. Right, you can either do this by yourself or with a team. And collaboration is always fun. And, you know, in the field, critical thinking and teamwork is an essential skill. And it's not just an essential skill for geoscientists. It's an essential skill, full stop, for anyone. Okay? And here you can see, obviously, people working together. There's my two friends here that I worked with a little bit a while ago. And this is us in Canada. You know, if people tell you you can't, you know, do field work in the snow, they're wrong. You take a little brush and then you just brush up all the little snow off the rocks, and you can still see the rocks. So there you go. Now, there's also time to appreciate the beauty of nature. Like, I was out there doing field work, and boom, out of nowhere, I had these beautiful, little, perfect snow flakes. I don't know if you've ever seen this in real life with your own eyes, but this I was blown away. I'm not going to lie to you guys. I was absolutely blown away. This is with my naked eye, by the way. I'm not using any fancy microscopes. You know, this is literally with my phone. Just like, wow, this is amazing. Like, all the snow that was coming down was like perfect crystals. I will never forget this experience. Again, these little moments you don't have if you sat in the lab. Not that you don't sit in a lab as a geoscientist, but you get to have best of both worlds. Now, when you're in the field, okay, FYI, this is my friend. He accompanied me because this area is quite dangerous, but it just gives you a sheer size of the scale of some of these like beautiful mountains and the geology that's really at play, like the bombastic nature of what's really going on below our feet and what's been going on for millions and billions of years and what's going on everywhere in the universe, right? Beautiful. Now, this is me. Once you're in the field, you're looking around, you know, you're looking for rocks, and, you know, sometimes you take breaks. Quick side note. You know, I've shared lots of pictures with my family and friends, etc. And then they're like, oh, why are you just laying around all day? Like, it doesn't seem like you're doing much field work. It's like, well, the only time you actually have time to take pictures of anything is when you're taking a break, right? So that's why all the pictures always look like, oh, these guys just have an easy job. But it's actually quite tasking. But anyway, you're looking at rocks and you're finding them. You take out your notebook and you start identifying features. You start noting down, you know, what does the rock look like? What is the color? You know, you use your notebook. It's almost like it actually is a diary. That's what it is. Right? But you don't say dear diary, right? You just write scientific notes. And these are fairly standardized across geosciences, so people can, you know, I could give my book to, you know, someone in 20 years' time, and they should be able to go to the same rock and get the same descriptions as before. So that's kind of how useful these books are. Okay, you draw landscapes, you draw ideas and models in your head, like, okay, how did this work? Again, this is all the 3D critical thinking that you need to use. And also, these are my best drawings, so please don't laugh. Okay, like I tried my best to do this. Again, here I'm trying to sketch this this mountain here again. Please don't laugh, okay? Because this is I'm really bad at drawing. But do you remember earlier in the slide I showed you all the composition of what geoscience is, at least for me, and art was one of them? This is why. Because if you have better art, you can pick out all the scientific features more easily, and you can present them better, you know. Now, once you've got all your rock data, or you collected all the information, you then take your topographic map, which is just a map depicting height, okay? You take your color pencil and you start shading in areas of that correspond to the rock, right? So here, again, my coloring in skills are like a good 3 out of 5, I would say. But you see here, there's like brown, all this brown, right? That's all one rock. That's all one rock type, okay? And then I've got my yellow here. Again, that's one rock type. All this purple here, it's a bit difficult to see from the red, but it's all the purple, one rock type. You know, the blue, one rock type. And here I've got notes, annotations, I've got data on there, and these are actual data that you can use in computers, etc. And I'll get to that in a second. Again, another one of my drawings showing, you know, like labels and diagrams and little labels and stuff, okay? Again, I'm not the best at coloring in. Now, when you get back from the field, you have to cook for yourself, of course, right? So, unless you're Nils and you empty the goddamn entire bag of rice on the floor, just like that. I always, you know, sat on the couch, I was like, hey, Nils, what we're going to have tonight? And he's like, oh, I think I'm going to have some rice. And then he, like, opens the bag, puff, and then all the rice goes everywhere. And I was like, God, man.
Yeah, that's what happened. You work together for, like, weeks, or should I say months in the Alps. Fun stories.
Yeah. So once you've eaten, you get some more work done, right? So you plug in your laptop. All right, that's right. So this is my laptop charger right here. And I bought my laptop in Canada when I was doing my year abroad, right? So I have my Canadian plug. So I've got Canadian to UK, and then UK to EU, and then EU to Switzerland, right? Because I thought EU has the same plugs as Switzerland. Not always, sometimes, but not always. Again, this was, I don't even know this is like, if this was safe to do or not. Like, it's probably dangerous or something. But anyway, I thought it was a funny picture. Another picture, again, I was doing work, you know, at the end of the day, you know, I'm working on my notebook with my maps and I'm comparing, okay, did this make sense? Okay, maybe I can think about this, and I'm drawing up models like, why did this data, why was it all in this direction? What is the significance of this, you know? And then you all piece together slowly. You're literally like Sherlock Holmes, you know, but with other things. You've got a laptop, cup of tea, milk, obviously, and coloring pencils, all these important things. And of course, you get some downtime as well. So, you know, one of these days we've thought, you know, we've got such a beautiful area in Switzerland. Why don't we just take the table outside and eat? And this was gorgeous, like the view and the little lake and things. Oh, I must say, geoscientists get some amazing, spectacular views. And the thing is, most of these views, no one's ever seen before. And I think this is another sell for why geoscience is such a great subject, because like you get to see and be places that no one's ever been at. Anyway, you get all your data all together, and you can study them in a lot more detail. So when I was talking about you can compute things and put things on your computer and calculate them. So I've, you know, we made this 3D model of the area here. You can probably see that this mountain is this mountain here, and I walked everywhere, you know, and this took me about 28 days of pure walking in the field. We're talking long days in the field. Now, field work isn't your cup of tea. Well, you can also do shorter days if you want to. Myself and Nils, we like to challenge ourselves, okay? We don't like to go the easy route. There's lots of easy things that you can do for field work, but we chose the hard route. I don't even know why, but at the end of the day, we keeping ourselves fit. Yeah, of course, you got to send the samples back as well, okay? And I don't know if you guys ever tried to send like a chunky load of rocks. It's not going to be cheap. So yeah, that's the box down here of all the rocks that we collected. I don't even know why we did this, because the guy at the post office was like, "Oh, you guys sending rocks?" And we were like, "Actually, we are. This is exactly what we're doing." Yeah, there's rock here, and these are they're called thin sections, okay? And you know, you get your rock sample that you collect in the field, and then you slice a couple of microns.
I don't put my rocks in envelopes. I just put them in a bag, and then I carry that bag around with all my other stuff until my back gets sore.
Exactly, right? But like if you've got, obviously I had to have all my gear to go back home and send it to go back home to Edinburgh, right? So I needed to take all my gear back, all my like clothes, some food, etc., and then all those rocks. It's more than I think 23 kilos of rocks, just rocks, right? There's a lot of weight. But if you have a couple of rocks, you know, it's fine. But yeah, thin sections, right? You get your rock sample, and then you take basically a saw, and then you cut very, very, very thin slices. Very thin slices. We're talking microns thick, right? So these slices are 33 microns thick, right? And then we can shine light underneath and look at under the microscope. Very cool. I won't spoil it for you though. Okay, now let's talk about what me and Nils do, okay? Because it's actually quite interesting, I think. So we're looking at rocks from China, and you know, we've unfortunately not been able to collect samples ourselves because of COVID. So otherwise we would have taken these samples ourselves. So these samples were sent to us by our colleagues, and we've again made thin sections. So rocks from here, cut a little thin section here, and that's the thin section, right? And then if you look under a microscope, this is what you see, right? And then if you basically, again, take those thin sections and then you fire electrons at them, you can get far more detail, okay? And this is what a scanning electron microscope does, right? And this is an image from a scanning electron microscope, okay? And you look at this and we study it, and we try to understand what's going on. Now, another thing we're trying to do is, you've probably heard of CT scans. You know, you do it in a hospital to find out, you know, what's going on with your body. And it's a way to kind of, without destroying any tissue and matter, find out the three-dimensional structure of organs and your, you know, arms, etc., bones, right? Now, we can apply those same techniques to rocks, right? So here, me cutting a small cylinder out of a rock sample. And then we fire up the CT machine, okay? And the CT looks like this, okay? I'm stood here. Obviously, when the CT is active, you don't stand on it because it's very dangerous, because it basically fires a very condensed stream of X-rays at the sample, okay? And this plate at the back here records roughly, well, not roughly, precisely, what the X-ray travels through, okay? So it's kind of a weird way of taking a picture, basically using X-rays. Now you can see the cylinder here that we drilled out earlier. If you spin it, you can get a 3D view of the sample. And if you've ever been a CT scanner, you as the sample, you know, if you go to the hospital, you as the sample, you don't spin, but the actual CT ray will spin around you to get a 3D view. So here we can just make the sample spin. It's way easier because it's a small little cylinder. And this uses a lot of juice, a lot of power, right? Anyway, what are we looking at? Because I told you a lot of things that we're doing. Well, what are we actually looking at? So we're looking at a thing called stylolites and pressure solution seams. The name of the thing, like, what the hell is this? Well, let me tell you. We have a little package of rock, okay? If you just think about like rock itself, okay? And you apply pressure to it from, you know, let's just say for argument's sake, from above and below. And you have these, if you zoom in, you can see all these grains, right? If you zoom into rock, you have smaller components of that rock, okay? And let's just say that these are soluble materials, okay? Now, if you apply enough pressure to them, they will slowly dissolve some matter, okay? Now, and these sort of like flaky, platy minerals here, they don't like to get dissolved. So they won't dissolve under pressure, okay? So pressure happened, okay? And if you zoom in on this wiggly, squiggly line, you see that all the grains have started to like interlock and sort of like get closer and closer together. At the boundary, there's a little bit of fluid that removes some of the material of those individual grains, and they come closer and closer together. And that material, that all that juice almost that's being, dissolved out, is being brought somewhere else, okay? And the insoluble materials, so like these platy minerals that don't like to get dissolved, they basically form whatever shape they can, okay? And often you get structures that look very like jaggedy like this, okay? And we're studying those things, okay? We're studying those things in relation to ores, right? So rocks that contain metals. And why are we doing this? It's a very good question, right? Stylolites, pressure solution seams, okay? They are complicated 3D surfaces, right? Now, why are they important in enriching and ore processes? Well, that's what we're trying to figure out. If you think of these stylolites as highways for fluid to move through, you might have a potential pathway for gold, for example. This is also one thing we're looking at, to become more enriched. So you have one concentration of gold in one area, and because you've got all these interconnections of these wiggly lines, you can bring more material to that locality and therefore create a more valuable gold resource, okay? And that's kind of what we're trying to understand here. Whether that actually occurs, to what extent it occurs. Again, we're trying to push the boundaries. Okay, it's not playing. Very sad. Yeah. So this is a 3D scan. It's supposed to be a GIF. I don't understand why it's not playing.
Not my data.
Yeah, it's Nils' data. And yeah, it's not very clear what it looks like. But you can see all the little yellow dots. Well, that's potentially gold. All the sort of bluish, those are the stylolites, all these wiggly lines, right? And then the red is basically fool's gold or pyrite, okay? And we're basically trying to look at the relationship between, okay, if we have these surfaces, these 3D complicated surfaces, and the pyrite and like the fool's gold and the gold, like what's the relationship between all those? Like how close are they to one another? What's the relationship between the 2 or 3 different phases? That's kind of what we're trying to look at. So I hope that kind of answers on what we're trying to do. It might be a bit of a complicated topic to talk about. I tried my best to sort of explain it. And yeah, so this is a picture of us. We're trying to be a bit edgy here. But this is sort of, we did the mapping project together. So this is my area on the right and Nils was on the left. Coincidentally, like we didn't plan this. We planned it to a degree, but we didn't plan that this sign would exist that way. This was actually quite fun. And yeah, so we hope that, Geosciences gives you an idea of, this talk gives you an idea of what Geosciences is actually about. And now we weren't able to cover every single subfield that exists in geosciences. And I just want to quickly do my due diligence and basically cover and just quickly talk to you about some of them that I think are very important as well, and that are mentioned within the realm of geosciences. So if I just go from the top here, we've got archaeology and anthropology. Again, this is looking at humans and the interaction of, well, how did humans live and the civilizations that are involved in there. And again, there's a little bit of geology involved in this as well, because you have to look at like soils and all this kind of stuff, right?
If I quickly interrupt here,
yeah, go
archaeology, actually really needs geophysics. There's a huge amount of geophysics surveys that actually find archaeological structures and all that. So geophysics is huge in there.
Too right. Thank you for that. Astronomy, again, looking at the stars, universe, etc. Further, atmospheric sciences, I think that's very clear. Ecology, you're looking at sort of how the environment interacts with all the sort of fauna, so like animals basically, and how they interact with each other. How does the sort of environment reflect on this and vice versa? So it's a very complicated relationship, super complicated maths, anomaly, and statistical analysis, because nature is very messy, especially animals. Environmental science, right, which is kind of similar to environmental geosciences. So we're talking about things of, okay, if there was a mine that produced lots of water that was actually really bad, had lots of acidity in it, and might actually be damaging, you know, you'd probably call an environmental scientist and trying to figure out and remediate the problem by adding, for example, things like limestone to this issue to solve that problem, right? They also look at climate change, right, which is a very big thing. They are very much the new sort of forefront of dealing with the climate change as a whole. Geography, I think you understand this, again, physical and human geography, looking at the different relationships between, you know, people around the planet versus geography. Physical geography looks at more recent processes of rivers and glaciers. You've got geology, which you've extensively covered here, which are basically mapping, field work, understanding of how rocks interact with each other. You know, we've got geochemistry, which is again geology, but with chemistry focused. So looking at, you know, things from ocean chemistry and how that relates to rocks, etc., because there's all sorts of reactions that go on there. Geomorphology is very similar and builds upon the sort of physical geography side of things, and you can basically like, it's basically the features that are involved and the process involved. So you've got like you know, if you've got slopes of mountains, you know, you're looking at the angles and erosion rates, and again looking at more recent patterns, rivers, how do they actually work? Because it's not just a simple thing of like, oh well, there's water flowing one way and that's it. No, there's complex interactions within the fluid that needs to be studied. Geophysics and geodesy, again, geodesy is study of like the shape of the Earth and other planets, and geophysics, again, like Niels mentioned, looking at using physics and applying it to geological problems and geoscience problems. So things like, you know, looking at almost non-observable ways of seeing geology. Okay, glaciology, looking at glaciers. Hydrogeology, looking at how water interacts with the rock, right, and sort of the cycles involved. Hydrology, which is basically the study of water and how it moves just by itself, and the study of water itself rather than it being related to rocks. Limnology, I didn't know this one, so I learned something new the other day. This is the study of sort of terrestrial, so land-based water systems, so like lakes and I think to some degree rivers as well. Mineralogy, so again, when I mentioned, you know, that this in our project, that these small platy minerals that weren't being dissolved, right, those are minerals, and studying those in relation to everything else, this is basically mineralogy. It's very complicated, but very, very beautiful, because you get to see lots of pretty colors and you get to study crystals in a lot more detail, but there's a bit of a hurdle, I think. Yeah, it's a wonderful subject, and most geoscientists need to have some understanding of mineralogy to actually appreciate what they're looking at. Oceanography is basically what Niels was doing today, looking at how, you know, ocean circulation and currents interact with one another, how the atmosphere interacts with the ocean, how biology interacts with the ocean. And basically this is, again, part of environmental geosciences, you know, aim to understand how the climate works and how the climate has worked in the past and how we can use that for the future. Paleontology, I think I don't need to introduce this one, looking at the study of life before humans mainly, and dinosaurs and fossils that were pre-existing. We're talking about Cambrian explosion, all this kind of stuff. Like really, really, really beautiful subject because you get to see some really crazy, wacky animals, I would say. Petrology is a bit of a difficult one to explain, but I think you guys know the difference between, like, you've got metamorphic rocks, you've got igneous rocks, and you've got sedimentary rocks, and those are all different types of these are like the three main rock types.
I was once at a beach and then I found a piece of pumice, and then I
Oh yeah.
thought, since pumice is a volcanic rock, I tried to think of where it most likely come from, and I realized the nearest actively volcanic place is Iceland. So I thought, no way, that rock must have been floating in the sea for years, all the way down south from Iceland.
So either that, or it was from a very old volcano and it's just been carved out recently. But guess we'll have to see it to figure it out.
Yeah. But again, this is
Very good.
how oceanography works as well, because sometimes you might think that they might take years to come down, but because there's a specific type of current that goes exactly where you want, and like just in a couple of weeks, it might be at the beach. So it's understanding all the complex interactions. Petrology is kind of understanding the different types of rock, from my understanding. Seismology, again, leads into geophysics, studying waves within the rock. So if you've got earthquakes, the propagation of those waves and how they interact with rocks, and also fluids and semi-fluids and rocks. And this is actually how we understand how the interior of our planet looks and what the materials are in that planet. Soil science, I think, was very explanatory, self-explanatory, but very important, especially if you're looking at agriculture and when you're looking at environmental remediation. So looking at how to fix problems that are like contamination, etc. Speleology, again, a word that I came across only a couple of years ago, the study of like caves and stuff, which I think is really cool. So probably most of the things that you're looking at will be like limestones, because I'm pretty sure most caves are to do with carbonate dissolution, because they're so readily dissolved that most of the stuff you'll be looking at is limestone caves. Volcanology, again, something I started off with, looking at lava, volcanic explosions, eruptions, all sorts. On this planet, on other planets, it's a huge field, very popular, lots of people like it. It also comes hand in hand with sort of protecting people and sort of understanding how to predict earthquakes and also volcanic eruptions, because sometimes they might be linked. Again, environmental geoscience, I already mentioned this. Hydrogen capture and storage, which is, hydrogen capture and storage, which is basically hydrogen is the new fuel of the future, and how to store it in old oil reservoirs and gas reservoirs is a new study, because hydrogen, when it becomes basically in contact with the Earth, dissociates into H+ ions, which is what Niels covered earlier as well. So it actually becomes acidic. So the reactions need to be made sure that you don't have all this acidity kind of going anywhere or destroying and having leaks of hydrogen gas somewhere. So you want to make sure that everything is contained within one sort of place under the Earth. So very complicated study, but very, very, very lots of investment into this nowadays. Again, carbon capture and storage. This is a very similar approach, but instead of taking hydrogen, you basically funnel all the CO2 produced by factories, and then you basically funnel them into reservoirs, so like oil reservoirs, and just keep them there to kind of take away some of the CO2, and also take CO2 from the atmosphere and draw them in. Again, huge amounts of investment, and that's kind of the future for a lot of things. And there's ethical and policy making, so making sure that when things are being removed from the planet, that there's ethical policies involved, and like processes that are proper. Again, there's sort of like a combination of legal and geology, because like you can't just be a lawyer but don't have an understanding of geology, because like it's very complicated to do that because you don't understand how geosciences works, right? So kind of putting them both together is basically making this. Tourism and conservation. I think it's very, very self-explanatory as well. But there's so many more different fields, and I think every year there's a sort of unique combination, and that's where most of the research is nowadays, is combining loads of different fields. Okay, and this is how we push the boundary of science, right? So if we think about actually the job market for geosciences, most of the people who are working currently as geoscientists are just before the retirement age. So there is a huge, or that there will be a huge gap in the market for geoscientists throughout the world, because the majority of them currently will be retiring. But we are seeing that geosciences basically is undersubscribed in a lot of universities, and we're trying to understand why, because we think it's a really fantastic subject, or like umbrella subject, right? Because it basically includes everything you ever wanted in a science degree, in a STEM degree, and more. You get to be outside, you get to be in the lab, you get to be with people outside, with friends for long periods of time, you get exotic places, you get to do like crazy science and stuff, and pushing boundaries and actually helping the environment. I think it's wonderful. And I think a lot of the times geology and geosciences gets a bad rep for the oil industry, which we can obviously understand, but we've got to appreciate that, we're trying to move away from this. And most of geoscience is actually catered towards fixing our climate change problem. So we're actually part of the solution here. So that's, I think, one of the take-home messages. Basically, I'm just going to show you real quick. This is just for officiality. These are all the images that were in the slideshow that were taken from the internet, and they're all Creative Commons. And so just that they're there for people to see, and also images from slides 11 to 29 and 62 to 72 are influenced by the University of Edinburgh content, so they should be fine as well. Well, this would be the end of the presentation in terms of the recorded part. So I'm going to stop recording now. What can I do with this?
Top left. I can stop it. I'll stop it.
Okay, stop recording. Yeah. I see.